Maximum flow is a graph problem. We have a source, called S, and a sink, called T. Each directed edge shows current flow over capacity. Capacity is the most flow that edge can carry. The goal is to send as much total flow as possible from S to T without exceeding any capacity. This model appears whenever limited capacity controls movement, network bandwidth, traffic and shipping routes, and matching work like assigning people to jobs or students to seats. Each green route is an augmenting path from source to sink. The amount we can send on that path is limited by its smallest remaining capacity. After each route, the total flow increases. Edmonds-Karp is the disciplined version. It is Ford-Fulkerson where each augmenting path is chosen by breadth-first search. Ford-Fulkerson keeps repeating one idea: choose an augmenting path from S to T in the residual graph. For path S to A to T, the smallest remaining capacity is 2, so we can send 2 units. After sending flow, subtract it from each forward edge on the path, and add reverse capacity so flow can be undone later if needed. Choose another augmenting path. On S to B to T, the bottleneck is 2, so total flow becomes 4. One last path remains, S to A to B to T. Its bottleneck is 1, bringing total flow to 5. Now no positive capacity path can reach T from S, so Ford-Fulkerson stops. Here is why reverse residual capacity exists. If we first send flow through A to B, that edge becomes full. A later residual path can use B to A, which means undo the earlier A to B flow, then reroute through A to T. Edmonds-Karp makes Ford-Fulkerson concrete. Always use breadth-first search to choose the next augmenting path. Start BFS at S. From S, both edges to A and B have remaining capacity, so A and B enter the queue. From A, T is reachable, so BFS chooses the shortest path S to A to T. BFS gives a previous map: A came from S, and T came from A. Walk backward through previous to compute min of residual S to A and A to T, which is 2. Then decrease those forward residual entries and increase the reverse entries. Run BFS again from S. From S, both A and B are still reachable. But edge A to T is full, so BFS skips it. From B, T is reachable, so the path is S to B to T. Again, previous records B came from S, and T came from B. The backward walk gives bottleneck 2, so forward residuals go down and reverse residuals go up by 2. Run BFS a third time from S. Now S to B is full, so only A is reachable from S. From A, B is reachable through the remaining edge. From B, T is reachable, giving path S to A to B to T. This time previous links are from S, B from A, and T from B. The backward walk gives bottleneck 1, so each forward residual on that path drops to 0 and each reverse entry gains 1. Final BFS starts at S, but no outgoing edge has remaining capacity, so T cannot be reached. A final BFS cannot reach T through positive residual capacity, so Edmonds-Karp stops. Ford-Fulkerson with integer capacities can take O of E times F, because each augmenting path scans edges and may add only 1 unit of flow. Edmonds-Karp uses BFS for every path. BFS is O of E, and the shortest path rule gives O of V times E squared overall. Both use O of V plus E space for the residual graph and BFS state. The main loop starts with residual capacities copied from the graph. BFS returns previous, a previous node map for the path it found. If T is not in previous, there is no path. Otherwise we walk backward from T to S once to compute the bottleneck, then walk the same path again to update residual capacities. The BFS helper only follows edges with positive residual capacity. That is why saturated edges disappear from the search. It stores previous of V equals U, meaning U is the previous node used to reach V. When T is found, that map reconstructs the shortest augmenting path by edge count.